Hi guys, welcome back to INTH. It's not that hard. Today we'll be learning how to find the second derivative of a parametric function as well as the tangent, or finding the concavity in the equation for a tangent line. First, we just need to recall that the derivative of a parametric function is the first derivative is just dy over dt over dx over dt. So you take the components y and x, divide them. And then now what's new is the second derivative. And all it is, it's fairly simple, it's just the derivative of your first derivative with respect to t, as what this says, divided by dx over dt. So you take this, you're going to plug it in here, and then you're going to take the derivative with respect to t, and then you're going to take this guy and then plug it in here. Fairly simple. The proof is not that important, but it's really not that hard. So d over dx, another way we can write it down, since we can treat d and x kind of like a variable, we can rewrite this as d over dt times dt over dx, and then this is of dy dx. We're keeping the other thing the same. This is allowed because, you know, you could treat dt and d almost like variables, and the dt's would cancel out and give you d over dx. So we're saying the same thing. We're just kind of breaking it apart. And then to make this match this, we just do d over dx of dy over dx, and then we can put this in the denominator and then flip, so we get dx over dt. So now we get the same thing. Very basic proof, not too important to know, but it's nice to get used to playing around with the dx and dt's. Okay, so we're going to jump straight into an example. Okay, so example 1, find the second derivative where x is equal to sine of t and y is equal to cosine of t. It's fairly simple. We just follow the steps. First, we have to find our first derivative. So in order to find the first derivative, we need to find dy over dt and dx over dt. So let's start with dy over dt. Derivative of cosine, or taking derivative of this with respect to t, will give you negative sine of t dt, respect to t. And then for dx, we're going to get derivative of sine of t is just cosine of t dt. And now we just have to divide these two to find our dy over dx. This should be covered in another video if you don't remember how to find the first derivative. And then this is almost redundant to write. You don't have to on the AP or anything because they cancel out anyways. And if we remember our trig identities, sine over cosine is tangent, so this will equal negative tangent t. So we found our first derivative, which is equal to negative tangent of t. Now we have to take this, derive it again with respect to t, and divided by dx over dt. So as a reminder, d2 over what? Or dx squared is equal to derivative with respect to t of our first derivative divided by dx over dt. Let's plug it in. Derivative of negative tangent theta is, you kind of just have to remember this, is, well, derivative of tangent theta is secant squared theta. Or, my bad. The derivative of tangent t is secant squared t. If it was theta here, it would just be secant squared theta. There's a negative sign here, so we make sure to keep that in mind. And then dx dt, we solved it. We're just going to plug it back in, and negative cosine of t. And now our job is, eventually it won't matter when we're determining concavity, but if they don't give you like a t value to compare, it's best to keep the dy over dx and the second derivative in terms of x or y, or both. In this case, we can rearrange this to put it in terms of y. So first, these negatives cancel. Secant is equal to 1 over cosine, so we can put secant squared as 1 over cosine squared, and then since we have a cosine here already, it's cosine cubed. And looky here, cosine of t is equal to y, so we can label this as y to the third. And congratulations, you just found the second derivative of a parametric function. Now we're going to do one more example, except this time we're also going to find the equation of a line or a tangent line to a parametric function, as well as determine concavity. Alright, let's do this second example. Find the equation of the tangent line where t is equal to 0 for the parametric function, where x is equal to e to the negative t and y is equal to e to the 2t, and then determine concavity at t equals 0. So, formula for a line with a point slope form is y minus y initial, m times x minus x initial. The pieces we need to fill in here are y initial, our slope, and then x initial. So let's find our slope first. Since this is a parametric function, our slope is going to be the derivative of the parametric function. And then to find the first derivative of a parametric function, we first have to find dy over dt and dx over dt. These are fairly simple. Derivative of e to the 2t is going to be equal to 2e to the 2t. That's just simple chain rule. Derivative of the outside, e to the 2t, e to the 2t. And then derivative of the inside, derivative of 2t is 2, so you got a 2 there. If you need help on chain rule, there'll be a video on that as well. And then dx over dt, simple, is also just negative e to the negative t. Cool. And now we have to divide these two. So dy over dx is going to be equal to 2e to the 2t over negative e to the negative t. So we got this far. Now let's just simplify, and this will become negative 2e. Oh, so this is really sloppy, but this is sorry, my bad, equal to negative e to the negative t. So we simplify and we get negative 2e to the 3t as our dy dx. Cool, we solve for that. Now we gotta evaluate it at our point. So we have to find it when t is equal to 0. T is equal to 0. Plug in t here. E to the 0 is just 1, so our slope becomes negative 2 is equal to our m. So we're going to plug that here. Next, we have to find our y initial and our x initial. That's simple. You just take these and then plug in t is equal to 0. So x1, when t is equal to 0, is just going to be e to the 0, which is equal to 1. And then y1 is just going to be same thing, e to the 0, which is equal to 1. This was a fairly easy example. We plug these in, and then our equation for the tangent line becomes y minus 1 is equal to negative 2 times x minus 1. Cool. So we did the first part of the function, the question, and we found the equation of a tangent line. Next, we need to find concavity. And if you guys remember, to determine concavity, we have to use the second derivative test. We'll do another video on that too. Essentially, all it is that you take the second derivative of and you determine at the point, or at some time t is equal to 0, if it's greater than 0, equal to 0, or less than 0. If it's greater than 0, you're concave up, which is positive concavity. If it's concave down, that would be when it's less than 0, and if it's equal to 0, you have a point of inflection. So let's find first the second derivative of our function. So if we know that this is our dy over dx, we know this is dx over dt, all we have to do, take the derivative, or here, let me make it clear, our second derivative is going to be derivative with respect to t of negative 2 e to the 3t divided by dx over dt, so negative e to the negative t. So simple enough. Now we just have to evaluate the derivative of negative 2 e to the 3t is just going to be negative 6 e to the 3t, and then we divide it by negative e to the negative t, and then simplifying we just get 6 e to the 4t. And then remember, when we can, we're going to try to put it in our y. So if they asked you to find what the second derivative is, you could plug this back in and get 6y squared. But at this point, it's actually better to keep this one because we need to determine concavity, and we're not giving y or x value, we're giving t is equal to 0 values. I guess you could plug in 1, but, or, no, you couldn't. You'd have to scratch that. You just have to keep your 6e to the 4t and evaluate it when t is equal to 0. So 6e to the 4t evaluated at t is equal to 0 is just going to be equal to 6, which is greater than 0, therefore concave up or a minimum or positive concavity. I believe all of these work, but I think concave up is probably the safest, then positive concavity, and then if they ask for the minimum, just say the minimum. And we could also, like I said earlier, it's there's no reason to, that's why I said scratch that, but you could plug in your y value at t equals 0, which we said was 1. You get here, it'll equal 6. So it's the same thing. But I would just stick with this way. Just do less work when you can on the AP. It's a time-sensitive test. Well, I won't waste any more time. That's all I have for today. Thanks for watching, and hopefully this cleared a few misconceptions. Bye.